In this video, I want to revisit the idea of p-values because this is a notoriously tricky and a little bit subtle idea. And I want to do this in the context of some data. So suppose that you have some data that you collect. And so say just for convenience that we have 6 data points, and those data points are 1.0, 2.2, 3.1, 3.2, 3.5, and 4.1. So suppose we have these 6 data points. And suppose that there's a researcher who wants to run a hypothesis test. And I'm not going to write this in a lot of detail, but say that the researcher wants to understand the hypothesis that prior research suggests that the population mean should be 4. These are the data points that the researcher collected. She wants to understand whether or not this is true, whether or not the mean is 4 or not. So the alternative hypothesis is that the population mean is not equal to 4. This is therefore a two-sided hypothesis test, or two-tailed hypothesis test. And what we want to do is I want to talk about the p-value of our data set. Now, in general, the p-value, so this is, it means it's not imprecise in the sense that it doesn't mean anything, but it means different things based on the context. So I think that's where the confusion is. The p-value is the probability. So p-value is the probability that randomly selected data, so that the randomly selected data from whatever distribution you're starting with, so that randomly selected data is at least as extreme as the data you have. Okay, so essentially this is a measure of how likely or unlikely were we to get a data set that looks like this. Okay, and so that's measured by the p-value. Now, the wiggly part of this, the fuzzy part of this, is the extreme. And what that means in this context, since our alternative hypothesis is that mu is not equal to 4, extreme means away from the population mean. So let's do an example here. So using this particular data set. And what I'm going to do is I'm going to copy this data set into R. Okay, so I'm going to copy this into R. And let's jump over in that case. And what we're going to do, well, let me just say what I want to do here is that this is going to be a z-test problem. We're assuming that the underlying population standard deviation is going to be 1.2. I want to do this for the z-test first, and then we'll come back and we'll do this for the t-test. If we get the z-test first, I think that'll be like 95% of the issues will be resolved there. So let's assume that the underlying population has a standard deviation of 1.2. And again, I didn't give you any context for what these numbers mean. Whatever, it doesn't, whatever, they can be whatever you want them to be. So what I want to do is I want to compute the p-value of this data set. And what we're going to do is we're going to remember how to compute the standardized score. And this is the formula that we have talked about in chapter 9. The standardized score, which we call z naught, is denoted by the sample mean, which is x bar, so that'd be the mean of these 6 data points, minus the population mean, assuming that the null hypothesis is correct. So what we mean is, say that the null hypothesis is correct, and we say that the mean is 4. So that'll be 4. And then we're going to divide by the standard deviation of the sample, but actually what we're going to divide by is the standard deviation of the population divided by the square root of the sample, which we learned from chapter 7. So we're going to divide by, in our case, 1.2 divided by the square root of, we have 1, 2, 3, 4, 5, 6 data points. Okay, so we're going to have the mean minus 4 divided by 1.2 over square root of 6. And the mean I calculated ahead of time is 2.85 minus 4, so it's divided by 1.2 over square root of 6. And that works out to be negative 2.347, just rounding to 3 decimal places. And so here's a picture that I think will help us. Okay, so here's a picture that will help us. what I want to do is I want to think about, say you have your normal data set or normal distribution. Negative 2.34 is probably somewhere over here. And at least as extreme, I want you to concentrate on that phrase. At least as extreme in this context means what's the probability that your data was at least this far away from 4? Okay, and so there's two ways to be this far away from 4. You can be over here, or there's also the positive terms. So all data that you would collect that would have a standardized value in that region would also contribute to the p-value. So the p-value is going to be the sum of these areas. So this area is 0.00945. This area by symmetry is exactly the same because we know that the normal distribution is symmetric about the y-axis. So the area to the left and the area to the right are equal. And so that means that our p-value is going to be the sum of those values or twice the value. So it's going to be 2 times 0.00945. And I got this p-value in R. The code that you would use in R to calculate this p-value would be, you want to calculate p norm. There's two ways that you can do it, and I'll explain both of them. A p norm of negative 2.347, and then that would give you this area. So it's the cumulative probability up to this value. So that would be this area, this region, plus the area of the other region. So you can do plus 1 minus p norm 2.347. The reason for that is that p norm of 2.347 without the 1 minus in front refers to the area to the left of 2.347, which is 1 minus the area that we're looking for. So we have to subtract that from 1. Or I think a much easier way to do this is just 2 times p norm negative 2.347. By symmetry, you know that the areas are equal, so just double the area. And so that's how you get the number 2 times that. So it turns out that your p-value is 0.019, and I've rounded here, 8925. So it's 0.018925. 25. Okay, again, however many decimal places you'd like. But that's how you get the p-value. So the p-value in this context is the sum of these two areas, because data point, the data that would give you a standardized value in these regions would be at least as extreme, at least this far away from the population mean. Okay, so that is how p-values work in that context. Now, let's do one more p-value problem. Let's look at the p-value for another data set. Okay, so let's suppose that we want to run another data set, and what we're going to do here is we're going to work with the data. We're going to work with the data. These are all just integers: 1, 3, 4, 5, 5, 6, 6, 9. So here we have 8 data points. We're going to run the null hypothesis test that mu is 5. The alternative will be that mu is less than 5. So this is going to be a left-tailed hypothesis test. And what's going to happen here? Is we're going to use the same formula. And so our standardized score, Z naught, is going to be the mean of this set is 4.875. So that's the mean, minus the population mean, which we're assuming is that we get from the null hypothesis, which is 5. divided by, suppose that the standard deviation of the population is 0.8. I forgot to say that. So 0.8 divided by the square root of 8 in this case. And what we end up with when we do this is negative 0.4419. So negative 0.4419. And what we're going to do then is we're going to think about how would this translate to the standard normal. So here we have the standard normal, so with mean 0 and standard deviation 1. And we just found negative 0.44 just somewhere over here. So negative 0.4419. Okay, and so we want to know what's the p-value, and it's going to be just this area. We don't have to worry about the area to the right because this is a left-tailed hypothesis test. So the probability that the data is at least this extreme means that it's at this point or to the left of this point. Okay, and so we want to know what's this area of that region. And it turns out that the p-value for this data is going to be p-norm of negative 0.4419, which it turns, I mean, that's the R code, and that turns out to give us 0.324. I'm sorry, 0.329. Okay, and that's how we would compute the p-value. So for a left-tailed test, the p-value is just the area of the left region. For a right-tailed test, the p-value would be just the area of the right region to the right of the standardized value. And for a two-tailed test, the p-value is the sum of the two areas, okay, to the right of the standardized score that we get if that's positive. So let's say to the right of the absolute value of the standardized score and to the left of the negative absolute value of the standardized score. Okay, so on either side there. So that's how that's going to work. Okay, so that's an overview of the p-value. One last thing that I want to explain. We need to decide basically when we run these hypothesis tests, we have two choices. We can either reject the null hypothesis or fail to reject the null hypothesis. When we reject the null hypothesis, what we're saying is that we have enough data to say that the null hypothesis is wrong in whatever context we have. And we reject the null hypothesis when the p-value is less than or equal to your significance. Okay, so this p is the p-value, and this alpha is the significance. So the significance is given in the problem, but you want to run this test with a 5% significance is generally what people do. 5% is small enough that you only get a few errors every time you do this. So if you were to run 20 hypothesis tests, you would expect meaning in terms of expected value, like we talked about in chapter 5. You would expect 1 out of 20 tests to give you a wrong value just out of randomness. But 0.05 is big enough that you're not being so stringent that you're kind of weeding out all the good data too. So yeah, so some links that you have, some sort of tests, you have to kind of make a decision. And if you are if you're too strict on making the decision, you're not going to reject the null hypothesis very frequently. Okay, so you'll err on that side. Maybe you should have rejected it more frequently than you did. Okay, so you'd make type 2 errors. If your alpha or your significance is too high, then you're going to make more type 1 errors because you're going to incorrectly reject the null hypothesis more frequently than you should. So it's a balancing act. Okay, is to eliminate the 2 errors. But the point is that you reject the null hypothesis when your p-value is less than or equal to your significance. You fail to reject when your p-value is greater than the significance. Okay, and that is the gist of hypothesis testing with p-values. In the next video, I will do some actual examples with data over how to run these tests using R.